Chapter 9, Molecular Orbital Theory. In this chapter, we're going to study basic molecular orbital theory, particularly for diatomic molecules. And we're going to see how this can be used to explain molecular properties, including bond length, bond energies, etc. We start with the simplest molecule, the hydrogen ion, where we have two protons, proton A, proton B, and one electron. The Hamiltonian operator contains the kinetic energy operator for proton A, proton B, and the electron. And the potential energy operator due to the attraction force of the electron with proton A, proton B, and the repulsion force between the two protons. Due to the complexity of this Hamiltonian operator, approximations have to be made. And one is the Bohr-Oppenheimer approximation. Under this approximation, protons move much slower compared to electron because it's much heavier, and therefore we can only consider the electron movement, and therefore we can assume the distance of the two protons is fixed, and we can solve the Schrödinger equation for the electron. And the solved energy is therefore a function of the bond length. Here shows a comparison of molecular wave function and the atomic wave function. When the distance between the two nucleus are far away, r is large, we see two isolated atomic wave functions or orbitals. When the two atoms or ions approach each other, distance decrease, we see a molecular wave function, which is a superposition of the two atomic wave functions. And therefore, we can assume the wave function of the molecule is a summation of the two atomic wave functions. The coefficients are to be determined. We just showed that the molecular orbital is a linear combination of two atomic orbitals. The coefficients are to be determined. For hydrogen ion, because two atomic orbitals are the same, and therefore we say the molecule is symmetric, and the two coefficient absolute value must be the same. And so two possibilities. The coefficient either are exactly same or have opposite sign. And therefore, two possible molecular orbital can be written as one is the two atomic orbital adds together, or the two orbitals subtract from each other. Now, for the first one, we give a sign called Gerard. Gerard means it's symmetric in terms of inversion. So if this is the center and two sides are exactly same, so when you invert one to the other, you get the same number, and that's called symmetric in terms of inversion, and this is called Gerard. However, if two sides are opposite sign, so if you invert from one side to the other, you change sign, and this is called anti-symmetric in terms of inversion, and that is un-Gerard. For the first molecular orbital, because they have the same sign, and so it's symmetric in terms of inversion. So this molecular orbital is called the Gerard orbital, molecular orbital, and the other one is un-Gerard. So when the wave function of the molecular orbital is one atomic orbital minus the other. We just showed that the molecular orbital is a linear combination of atomic orbitals. To solve the coefficient, we use normalization condition, and that is the integration of the wave function of the molecular orbital, which is a combination of two atomic orbitals, the conjugate, times the molecular orbital of itself should equals to 1. So expand this product, okay, and we've noticed that when the two atomic orbitals are the same, and this is just the normalization for wave function A, so that's 1, and this is the normalization wave function normalization condition for atomic orbital B, and so that's also 1. Okay, and notice the third one is a product of two different wave functions. One is on A, one is on B, and so this is called overlap integral, which we can draw like this: two wave function. So this is A. Let's say this is A, this is B. Now, when the two wave function has no overlap, they are far away, then the product integration will be 0. And so the larger the overlap, the larger this integral. So this integral depends the overlap of those two wave functions, and that's why it's called the overlap integral. Okay, so now the normalization condition becomes 2Cg times 1 plus overlap integral. Cg is the coefficient of the Girard wave function. All right, so for this to be 1, and Cg can be calculated, and therefore we can find the molecular orbital for the Girard molecular wave function is when the two atomic orbitals has the same sign. Similarly, we can solve the un-Girard coefficient, and when the two wave function has different sign. And notice that both the wave function depends on the overlap integral. And it turns out that this overlap integral plays an important role on the formation of molecules. And later, we're going to see that the energies of these molecular orbitals also depends on the overlap integral. Here shows how molecular orbitals look like. The Girard wave function is formed by two atomic orbitals that have the same sign when they add together, and you can see the two sides are symmetric in terms of inversion of this molecular center, and so that's why it's called Girard. It's symmetric. On the other hand, for the un-Girard, when the two wave functions have different sign, okay, positive, negative, so it's anti-symmetric in terms of inversion of the center. Now, it's important to notice that if we square this wave function, we get this probability distribution. And it is important to see that the probability of the electron between the two protons, okay, is 0. Okay, there's nodes between them. And so the probability between the two protons are 0. And this is opposite to the concept of bonding. Because when the atoms bonds together, you should have electron sharing between the two nucleus. But here, there's no electron between them. And therefore, this is called the anti-bonding orbital. All right. So when the two atomic orbitals have different sign, we form anti-bonding orbital. And the molecular orbital that has the same sign of the atomic orbital, and this is called bonding. And you can see there's a significant amount of probability of electrons in between the two between the two protons. Here again, we show two molecular orbitals. For the Girard wave function, we see the wave function are symmetric in terms of the center. Okay, and also we see significant electron density between the two protons. On the other hand, for the un-Girard, we see opposite sign, and so there is anti-symmetric in terms of center, and there's no electron between the two protons, so it's anti-bonding molecular orbital, and this is bonding, and this is anti-bonding. In order to calculate the energies of molecular orbital, we use the equation for expectation value. In this equation, here is the molecular orbital wave function conjugate, Hamiltonian operator, and molecular orbital wave function. So plug in the molecular orbital wave function, which is a linear combination of atomic orbital, and expand it, and so we get these two energies that involves several integrals. So we have overlap integral we already talked about before, and we have some new integrals need to calculate. HAA is when the two wave function atomic orbitals are the same with a Hamiltonian operator, and here it's HBB because two atomic orbitals are the same with Hamiltonian operator, but these two are the same, so combined together. And here this is HAB and this is HBA, and they are the same. So we have this equation. So this is the energy for Gerard, and this is energy for un-Gerard. So both of these energies involves the calculation of three integrals. So overlap integral, HAA, HAB, here also HAA, HAB. So because of time limit, we are not going to details into the calculation, but the next two slides just briefly show what is HAA, what is HAB. So this shows the HAA, and in order to calculate HAA, you need energy of s orbital plus the calculation of E over 4 pi epsilon r and a J integral, okay, is this one. So HAA is the energy of a hydrogen atom interacting with a proton at a distance r. And here is how to calculate the HAB, which involves a K integral. Okay, so K is a measure of interaction between a nucleus and excess electron density in the internuclear region arising from overlap. Okay, so here is a comparison of the calculated energy of the molecular orbitals and the experimental data. And you can see the calculated energy for the Gerard or the bounding molecular orbital has a minimum energy at a distance here, and that indicates that at this distance the molecule is a stable molecule, or this distance is the equilibrium bound length of the molecular orbital. On the other hand, for the un-Gerard or the anti-bounding molecular orbital, there's no minimum energy. The energy goes up all the way if the distance decreases, and that means there's no distance make the molecule stable compared to the atoms. So it's a anti-bonding state. And you can also see the experimental data resembles the theoretical calculation very well. In the last few slides, we showed very briefly how molecular orbitals can be calculated using linear combination of atomic orbitals. From now on, we only show qualitatively by drawing how molecular orbitals are formed. So when two atomic orbitals join like this, here we show s orbital, approach each other, they form two molecular orbitals. One is called a bounding molecular orbital when the two signs are the same, so the two atomic orbitals have the same sign, and an anti-bounding molecular orbital when the two atomic orbitals have different sign. Now, the anti-bounding molecular orbital, we use a star symbol to represent. This molecular orbital is anti-bounding. In the anti-bounding molecular orbital, there's no electron density between the two nucleus. In the bonding molecular orbital, there's a significant amount of electrons between the two nucleus. Also notice that the energy of the bonding molecular orbital is lower than the atomic orbitals. That means that when the atoms combine forms this bonding molecular orbital, it becomes more stable. On the other hand, the energy of the anti-bonding molecular orbital is higher than the atomic orbitals. And therefore, when the atoms combine forms anti-bonding molecular orbital, it becomes unstable. The difference between the atomic orbital and the anti-bonding molecular orbital is greater than the difference between the bonding molecular orbital and the atomic orbital. And that indicates that the energy loss, the energy loss when an electron in the anti-bonding is greater than the energy gain when the electrons in the bonding molecular orbital. One more thing is the symbol sigma. So in the bonding molecular orbital, if this is the molecular axis, so through these two nucleus, so that's the molecular axis. If the molecule rotate along this molecular axis, it doesn't change sign. And so this is called a rotation symmetric. And if a molecular orbital has this symmetry, a rotation symmetry, and that's called the sigma bond. And for the anti-bonding molecular orbital, this is the molecular axis, and when you rotate, and the negative is still negative, positive still positive, and therefore it doesn't change sign, it's symmetric, and so that's also sigma bond. So sigma bond is rotation symmetric. So for s orbital, the bonding molecular orbital, anti-bonding molecular orbital are both sigma bonds. They are both symmetric when you rotate along the molecular axis. Molecular orbital theory is very useful in explaining molecular properties. For example, we know inert gases such as helium, neon, argon, krypton, they usually form monatomic gas. That means they don't share with other atoms. And the reason is they have 8 electrons in the valence shell, and so the valence shell is 4. And so how do we explain that in molecular orbital theory? In molecular orbital theory, the two atoms combine forms 2 molecular orbitals. In helium, one s orbital has 2 electrons, so the molecule has 4 electrons. And due to the Pauli exclusion principle, 2 electrons go to bonding, 2 electrons go to the anti-bonding. The bonding molecular orbital has energy lower than the atomic orbital, so electrons go to the bonding will gain gain energy, but the energy of anti-bonding is higher than the atomic orbital, and so electrons go to anti-bonding will lose energy. The molecule becomes unstable. So the energy gain by filling electron in the bonding cancel energy loss by filling electron in the anti-bonding. In fact, in the last slide, we show that this energy loss due to the anti-bonding is greater than the energy gain due to the bonding, and therefore the whole molecule is unstable compared to the atoms, and therefore the helium atoms do not form diatomic molecules. In summary, when 2 atomic orbitals combine, they form 2 molecular orbitals. One is bonding, one is anti-bonding. The bonding molecular orbital has energy lower than the atomic orbitals. And the energy of anti-bonding molecular orbital is higher than the atomic orbital energy. The splitting of this anti-bonding delta E is greater than the splitting of the bonding molecular orbital. So far we showed the molecular orbitals formed by s orbitals. What happens if p orbitals interact to form molecular orbitals? Now we know there are 3 p orbitals, px, py, pz. So if two atoms approach each other, for example, if another atom is here, okay, so if this direction is z direction, so the two atoms approach each other along z direction, and what happens to this pz orbitals? So here shows that when this add together, if they have the same sign, then they forms a bonding molecular orbital, and if they have different sign, they form anti-bonding molecular orbital. Now these orbitals are sigma bonds, because if this is the molecular axis, when you rotate, it doesn't change sign. Similarly, the anti-bonding, all right, if you rotate, it doesn't change sign. And so that's both bonding, anti-bonding, and they are sigma bond for the pz atomic orbital forming molecular orbital. In the last slide, we show that when two atoms approach each other along z direction, okay, so this is z direction, then the two pz orbitals combine forms two molecular orbitals, both are sigma bonds. What happens to the px? Okay, so you see when the two atoms approach along this z direction, the px interaction is shoulder-shoulder interaction. So here shows the pz orbitals approach each other along z direction, and so when they have same sign, this is the bonding molecular orbital, and this is the anti-bonding where they have different sign. Okay, so now if you rotate along the molecular axis, yellow color becomes blue, blue becomes yellow, so it changes sign, and in other words, is anti-symmetric along rotation of molecular axis, and this is called a pi bond. So pi bond is anti-symmetric of rotation, all right, and the sigma bond is symmetric about rotation. Similarly, for the anti-bonding, so this is the molecular axis. When you rotate, again, yellow becomes blue, yellow becomes blue, blue becomes yellow, so they change sign, so it's also pi bond. So bonding is a pi molecular orbital, anti-bonding molecular orbital is also a pi bond. Okay, now remember, this is a px. Now there's another py perpendicular to it, and when these two atoms approach each other, the py also interact in a shoulder-shoulder fashion. So it gives you similar molecular orbital, but they are perpendicular. So if this molecular orbital is due to the px, and this will be the py that perpendicular to it, and this is also a pi bond. Okay, similarly, you have a anti-bonding molecular orbital due to the py interaction. So if you have three p orbitals, okay, when the other atom also have a px, so let's say px, py, pz, here px, py, pz. When these two atoms approach each other, the two pz orbital, they combine. Okay, so this is z, yx. So the z orbital forms sigma bond, and this is sigma anti-bonding, and the px forms a pi bond, and py also form a pi bond that has the same energy, and anti-bonding here due to the x, here due to the y. Okay, so they are pi bonds. So pi bonding, pi anti-bonding. Okay, we'll see more in the next slide. Here shows the molecular orbital diagram for period 2 diatomic molecules. Now we start from 2s atomic orbital. Remember, we also have 1s, but 1s is called the inner shell, and the energy is very low, so usually it doesn't participate in the chemical reactions. So we usually start with valence electron, and for period 2 we start with 2s atomic orbital, and the 2s atomic orbitals combine forms 2 molecular orbitals. One is bonding, one is anti-bonding, and the bonding is a sigma bond, because when you rotate it does not change sign. Same is the anti-bonding, and when you rotate doesn't change sign. The bonding molecular orbital also called Gerard, because it's inversion symmetric, and the anti-bonding is un-Gerard because it changes sign when you invert along the center. Now the 3p orbital, okay, so px, py, pz, if the atoms approach each other along z direction, then the pz orbitals forms sigma g bonding and sigma u anti-bonding. So in the bonding, the pz interact, head-to-head interact, and when you rotate it doesn't change sign, so it's also a sigma bond. All right, so it's a second sigma bond, and this is the first sigma bond, and this is the second sigma bond. So that's due to the pz atomic orbital. Now for px, it forms a pi bond. Okay, show the interaction. It's a pi bond because when you rotate, it changes sign, red to green, red to green. So it changes sign, so it's a pi bond. Same as this one coming from the py orbital interaction. So you have 2 pi bonds, same energy. It's better to draw like this. So you have 2 bonding pi bonds, and the px py also forms 2 anti-bonding. So 2 energy looks like this, and they are pi bond because when you rotate it changes sign and the energy is higher. Okay, so this is a complete energy diagram, and for the reasons we are going to talk about in the next slide, this energy diagram is suitable for oxygen and fluorine. The energy diagram for the lighter molecules up to nitrogen is similar to the energy diagram of oxygen, fluorine shown in the last slide. So the s orbital, okay, the 2s orbital combine forms 2 molecular orbital, bonding, anti-bonding, and then the p orbitals. In the last slide we show the pz orbital forms second sigma bond, so 2 sigma g due to the pz orbital, and then you have 2 pi orbitals due to the px py. However, for the lighter atoms, the energy levels are very close to each other, so this molecular orbital and this molecular orbital, they mix, they interact. The result is the energy of this one goes up. So the second sigma g actually has an energy higher than the pi orbital, the first pi orbital for lighter molecules as far as nitrogen. Okay, so the energy diagram here is suitable for the molecules formed by lithium, beryllium, boron, carbon, nitrogen. All right, and so this is one. The difference is the pi. Okay, the second sigma g is above the first pi molecular orbital. This shows orbital energies of periodic 2 diatomic molecules. As we already know from the last few slides, the first two molecular orbitals, 1 sigma g, 1 sigma u, are due to the 2s atomic orbital interaction to form these two molecular orbitals. The 2 sigma g, 2 sigma u are due to the pz atomic orbital interaction, and the 1 pi u, 1 pi g are due to the px and the py show the interaction. So they are pi molecular orbitals. For oxygen fluorine, the 2 sigma g are lower in energy than 1 pi u, but for lighter atoms, the 2 sigma g is higher in energy than 1 pi u, as we explained in the last few slides. Now, these energy diagrams are very important when we explain the molecular properties. We already explained why helium molecules does not form because it's more unstable than the helium atom itself. So let's explain whether lithium molecule exists. Does lithium molecule exist? Now, lithium has 3 electrons. Of course, only one valence electron. So 2s is the valence orbital, has 1 electron. Now you have 2 lithium, so total valence electron is 2, and therefore the 2 electrons both occupy the molecular orbital 1 sigma g. As we know, 1 sigma g is a bonding molecular orbital, 1 sigma u is an anti-bonding. Okay, similarly, 1 pi u is bonding, 1 pi g is anti-bonding, and 2 sigma g is bonding, and 2 sigma u is anti-bonding. So because 2 electrons both in the bonding molecular orbital, there's no electron in the anti-bonding, so the whole molecule gain electron by occupying bonding molecular orbital compared to the atomic orbital. And therefore, lithium, when they form molecule, lithium-2, it is more stable than the atoms. And therefore, lithium molecule do exist. Now, let's look at the beryllium. So beryllium, the valence electron is 2s2. So the total number of electrons if it forms beryllium-2 is 4 electrons in the valence electron. So 2 goes to 1 sigma g, which is the bonding molecular orbital. 2 goes to the anti-bonding molecular orbital, 1 sigma u. And therefore, the energy gain is cancelled by the energy loss due to the anti-bonding molecular orbital. In fact, it becomes more unstable, as we explained again before. And therefore, we expect beryllium molecule is not stable. Now, in the next few slides, we look at more of these molecules. Let's introduce a useful concept called bond order. Bond order is calculated by half n minus n star. N is the number of electrons in the bonding molecular orbital. N star is the number of electrons in the anti-bonding molecular orbital. So let's assume you have a bonding, let's say it's 1 sigma g, and this is 1 sigma u, which is anti-bonding. So let's assume you have 2 electrons in the bonding molecular orbital. According to this equation, so half 2 electrons is the bonding minus 0 in the anti-bonding, and that gives you 1. So we divide by 2 because each orbital holds 2 electrons. So this gives you an idea how many bonds formed in the molecule. So in this molecule, it has 1 bond because 2 electrons in the bonding molecular orbital. Now, if another 2 electrons occupy the anti-bonding, then you have half 2 minus 2. So 2 in the bonding, 2 in the anti-bonding, and then divide by 2, that gives you 0. So this molecule does not have any bond order. Okay, or in other words, it doesn't form a stable bond because the electrons in the bonding, anti-bonding, they cancel each other. So molecule does not gain any energy. Okay, so the bond order is a measure of net bonding in a diatomic molecule. Lewis dot structure indicates that there are 3 nitrogen-nitrogen bonds or triple bond. Okay, sometimes we draw like this. So there's a triple bond in the nitrogen molecule. So how does the nitrogen molecule look like in the molecular orbital theory? So first step, we choose the correct energy diagram. So this is the energy diagram for the lighter molecules up to nitrogen. Okay, so note that the 2 sigma g is above the 1 pi u. Now for oxygen fluorine, we would choose the energy diagram that 2 sigma g goes to here. Okay, so for nitrogen, this is the correct energy diagram. So second step, we count the total number of valence electrons. And nitrogen, each nitrogen have 5 electrons, so 2s2, 2p3. So 5 electrons for 1 nitrogen. Now 2 nitrogen should have 10 electrons. 2 goes to 1 sigma g, 2 goes to 1 sigma u, 4 goes to 1 pi u. Okay, because you have 2 pi orbitals. 1 comes from 2px, 1 comes from 2py. So total is you can feel 4 electrons, and then 2 electrons goes to 2 sigma g. This 2 sigma g is because of the pz orbital, and so if you count, that's 10 electrons, and we can write electronic configuration just like atoms. So you start from the lowest energy level. So 1 sigma g, 2 electrons, 1 sigma u, 2 electrons, 1 pi u, you can feel 4 electrons because you have 2 degenerate energy molecular orbitals. And then 2 sigma g, 2 electrons. So just from this, you can see 2 sigma g, 2 sigma u cancel each other, right? And these are all bonding molecular orbitals, okay? And the anti-bonding molecular orbital have no electrons, and therefore this molecule should be very stable. In fact, you have 3 bonding molecular orbitals are occupied by electrons. In fact, we can quantitatively calculate the bond order. So bond order is half n minus n star. So 6 is the electrons in the bonding molecular orbital, and star bonding molecular orbital is 0. Now, we didn't count these two because they cancel each other. Now we can add them together, give you the same answer. For example, how many electrons in the bonding? So here 2 electrons, here 6, right? So 6 in by p orbitals, 2 by s orbital. So you have 8 in the bonding molecular orbital, and minus anti-bonding. So this is anti-bonding, 2, and here 0. So divide by 2, and that give you 3 again. So you can count 1 sigma g, 1 sigma u, but you don't have to, because as long as they both occupies electrons, they cancel each other. So we only can count these molecular orbitals. So what does this mean? Bond order is 3. That indicates there are 3 stable bonds in the molecule. Okay, so that is consistent with the Lewis dot structure that you have a triple bond. Now, the molecular orbital theory gives you more information, because it tells you that 3 molecular orbitals are not equivalent, and 4 electrons are in the pi bonds and 2 electrons in the sigma bond. That's the 2 sigma g and 1 pi u. So they have different energies. So 6 electrons in the 3 bonds that are not equivalent. Okay. Here is an example to compare the dissociation energy of nitrogen molecule and nitrogen ion. Now, dissociation energy is the energy to break the bonds. So it's a measure of the bond strength. Okay. Now, in the last slide, we already showed the electronic configuration for nitrogen molecule. So in the nitrogen molecule, 2 electrons in the sigma g, 2 electrons in sigma u. So sigma u is an anti-bonding, so these two cancel each other. And then 4 electrons in the 1 pi u, 2 electrons in the 2 sigma g. These are all bonding molecular orbital. So more electrons in the bonding molecular orbital, more stable the molecule is. More electrons in the anti-bonding molecular orbital, the more unstable the molecule is. So we calculate the bond order is 3, all right, because here 6 divided by 2, and that's 3 bonds. So for N₂ ion, that means you lose an electron from nitrogen molecule. So when the nitrogen molecule lose electron is the highest energy level lose electron, and that's from 2 sigma g. Okay, and remember these two cancel each other, and so you now have 5 electrons in the bonding molecular orbital, no electron in the anti-bonding. So divide by 2, that gives you bond order 2.5. So bond order decrease, and that means the stable bonds decrease, and therefore we would expect that the nitrogen molecule has a larger dissociation energy, and N₂ plus has a smaller bond dissociation energy. The bond order smaller. Okay. In fact, the experiments show the nitrogen ion bond order, the dissociation energy 842 compared to 945 for nitrogen molecule, which has a triple bond. Okay, so we can compare fluorine and fluorine ion in the same way here. We have a homework that do other atoms and ions. Lewis dot structure predict that oxygen molecule has a double bond. How does the molecule look like in molecular orbital theory? So we choose the correct energy diagram for oxygen. and we calculate how many valence electrons. So oxygen in the group 6, so it has 6 valence electrons. So 2 atoms has 12. So 2 goes to 1 sigma g, 2 goes to 1 sigma u, 2 goes to 2 sigma g, 4 goes to 1 pi u, and then 2 goes to 1 pi g. That's total 12 electrons. So here is the electronic configuration. Now remember these two, one is bonding, one is anti-bonding, so they cancel each other. These 6 electrons are the bonding molecular orbital, and 1 pi g is the anti-bonding molecular orbital, and therefore the bond order, all right, you don't need to count these 4 electrons. So start from 2 sigma g, so you have 6 bonding molecular orbital, 2 anti-bonding. So 6 minus 2 is 4. 4 divided by 2 is 2. So bond order is 2. All right, that is consistent with the double bond in the Lewis dot structure. Of course, the molecular orbital theory tells us more about these molecules. So it tells us there are 6 electrons in the bonding molecular orbital, all right, 2 in the 2 sigma g, 4 in the 1 pi u. But there's also 2 electrons in the anti-bonding 1 pi g. Okay, so if you look at closely, 1 pi g has 2 molecular orbitals. They are very close. That means they have the same energy. In fact, it's better to draw energy diagram like this, same level, 1 pi g. Okay, you have 2 1 pi g, but you have 2 electrons. So how does 2 electron occupy 2 molecular orbital that has the same energy? All right. So according to Hans rule, the 2 electrons should occupy different orbitals with parallel spin, and therefore 1 electron goes to 1 orbital, the other goes to another that has parallel spin, and therefore molecular orbital theory predict that the oxygen has 2 unpaired electrons. These 2 electrons are unpaired. So if it's unpaired electron, the molecule is called paramagnetic. It is active in magnetic field. And so here is the experiment that liquid nitrogen, all right, when strong magnetic field is applied, the liquid oxygen will be attracted to the magnetic field. And if you do the experiment for other molecules, you don't see this. And so this is an example shows that molecular orbital theory is very useful to explain and or predict the molecular properties that Lewis dot structure cannot do. Bond order is a theoretical concept that can be calculated. How is this related to experimental data such as bond energy and bond length? So in this diagram, we show that when the bond order increase from beryllium, boron to nitrogen, okay, bond order increase, bond energy increase, okay, and when the bond order decrease, the bonds becomes weaker and the bond energy decrease. And force constant also parallel to the trend of the bond order. Okay, bond order increase, force constant increase. Bond order decrease, force constant decrease. Because force constant, okay, if you think about the bond as a spring, then the force constant tells you the strength of this bond. Okay, so force constant is a measure of bond strength. The bond length, on the other hand, is opposite to the trend. So when bond order increase, the bond length decrease, and when the bond order decrease, the bond length increase. and this is because a stronger bond is shorter, and the longer bond is a weaker bond. So when the bond is long, it's weak. And for example, carbon-carbon single bond, the length is about 1.54 pm. For double bond is about 1.34, and for a triple bond it's about 1.2. So stronger bonds, shorter bond length. Okay, so the greater the bond order, the greater the bond strength, the shorter the bond. Using molecular orbital theory, we can calculate the energies of molecular orbitals. Is there an experiment that we can measure the energies of the molecular orbitals? And the answer is yes. It's called Photoelectron Spectroscopy. So here we shine lights onto the molecules, and the light usually is UV or even X-ray range. So when the light comes in, the molecule will absorb the energy, and the electrons on the molecular orbital will be ionized, and the extra energy becomes kinetic energy. If we know the energy of the incoming light, that is HV, and if we also can measure the kinetic energy of the electron coming out, then we can calculate the ionization energy of the electrons. So here is a diagram shows that a lamp provides the UV or even X-ray onto the sample, and the electrons ionized becomes kinetic energetic and move out, and here you have an electrostatic analyzer that can measure the kinetic energy of the electrons. Okay, so by measuring kinetic energy, and we can calculate the ionization energy. Now Koopman's theorem says the ionization energy is equal to the orbital energy of the ejected electron. So this way we can measure the kinetic energy of the orbitals. And again, for the valence electrons, you need UV. Okay, it's called ultraviolet photoelectron spectroscopy, or UPS, and this is suitable for valence electrons. For core electrons, we use X-ray, so that's called XPS. Here is a photoelectron spectrum of nitrogen. The first line corresponds to 15.59 electron volts, and the origin of this line is due to the removal of electron from the highest energy molecular orbital, and that is 2 sigma G. The line with ionization energy 16.7 is most likely from the electron at 1 pi U. As we know, molecules also vibrate, and so the result is the vibrational fine structure. So far, we discussed homonuclear diatomic molecules, the molecules made of the same elements. What about the heteronuclear diatomic molecules? For example, hydrogen fluoride is made of hydrogen and fluorine, and usually the atom that is more electronegative, in this case is fluorine, has a lower energy than hydrogen. And now these two atoms combine also forms molecular orbitals. So one is bonding and one is anti-bonding. The bonding molecular orbital resembles the atomic orbital of the elements that is more electronegative. In this case is fluorine, and the anti-bonding molecular orbital resembles the atomic orbital of the elements that is less electron negative.